Welcome to the Explainer. Today, we're going to tackle a question in robotics that seems to, well, break a fundamental rule of movement. By the end of this, you'll see why, sometimes, adding more freedom is the only way for a robot to move at all.
All right, so let's just jump right in. Any single solid object, like a baseball or your phone if you toss it in the air, can only move in 6 basic ways in 3D space, period. So how in the world can a robot arm have 7 degrees of freedom or even more? This question pops up all the time, and the answer is actually a really core concept in robot design. To get to the bottom of this paradox, we first have to be on the same page about what we're even counting. So let's start with the official definition of a degree of freedom, or as you'll often hear it, DOF. The textbook definition sounds a little dry, but it's actually pretty simple. A degree of freedom isn't a type of movement itself, it's a piece of information. It's just the minimum number of numbers you need to perfectly describe an object's exact location and the way it's oriented. Think about a simple door on a hinge. It can only swing open or shut, right? So to know its exact position, you only need one single piece of information, its angle. That's it. One number means 1 degree of freedom.
Okay, now what about a coin on a table? Well, it's a little more complex. You need 2 numbers, an X and a Y coordinate to say where it is on the table, and then you need a third number for its rotation to say which way the head is facing. So that's 3 independent numbers, which means 3 degrees of freedom.
And all this leads us to the magic number 6. This is the absolute maximum possible freedom for any single solid object moving through the 3D world we all live in.
So 6. Why is it always 6? Where does this magic number even come from? Well, it breaks down really simply into 2 groups, 3 ways to move and 3 ways to turn. The movements are just forward and back, left and right, and up and down. And the turns are what pilots call pitch, yaw, and roll. That's the whole shebang. 6 total ways for any single object to get around in space.
Right, so if 6 is the absolute max for any single object, we're back to our original head-scratcher. Why on earth would a robot need more? And this is the key. This insight from a discussion on Reddit, man, it just nails it. The definition applies to the whole system. And a robot arm isn't one single solid body. See, a robot arm isn't one solid thing. It's a chain, a series of links all connected by joints. And each of those joints can move all by itself. So if you want to know the exact pose of the entire arm, you need to know the angle of every single joint in that chain. And there it is. That's the big aha moment. We've been talking about 2 completely different things without realizing it. The robot's hand, the part that grabs things, called the End-Effector, that part needs to achieve those 6 degrees of freedom to reach anywhere and be oriented any way. But the arm's total degrees of freedom is just a simple count of its movable joints. They're 2 totally different measurements. Okay, so if a robot with 6 joints can give its hand 6 degrees of freedom, that should be a perfect match, right? Case closed? Well, not so fast. It turns out sometimes 6 just isn't enough because things can get a little sticky. The problem is something called a kinematic singularity. It's a fancy term for when the robot gets its arm into a really awkward pose and basically paints itself into a corner. By lining up its joints in just the right or wrong way, it actually loses a degree of freedom at its gripper. It gets stuck. It's a lot like a famous problem in aerospace called gimbal lock. When the axes of a gyroscope line up perfectly, it suddenly loses the ability to rotate in one direction, which is not exactly what you want when you're flying something. It's the same basic idea. Okay, here is an awesome way to feel this for yourself right now. Straighten your arm out completely, lock your elbow, and then try to move your hand forward. See? You can't. Your arm doesn't know which way to bend from that position. That locked out position is a singularity. And that right there, that feeling of being locked, that is exactly why roboticists build arms with more than 6 joints. This extra freedom has a special name. It's called redundancy. So again, why go through all the trouble? Why add the extra cost, the weight, the crazy complex math for a 7th joint if 6 is technically enough? Because the answer is literally right in front of you. It's your own arm. From your shoulder down to your wrist, the human arm is a 7 DOF system, and nature gave us that extra joint for a very, very good reason. Seriously, try this. Put your palm flat on a table or desk in front of you and don't move it.
Now, even with your hand totally fixed in place, notice how you can still move your elbow around? You can swing it way out to the side or bring it in close. That movement, that is your 7th degree of freedom. That's redundancy at work. You see, that extra joint, that redundancy, it's like a superpower for the robot. It gives it the flexibility to just reposture its arm to avoid those locking singularities entirely. It can reach around an obstacle without even moving its hand. It gives it an infinite number of ways to position its arm to reach the same target, so it can pick the one that's the most stable or uses at least energy. It's a game changer.
So what's the big takeaway here? Well, the number of joints a robot has isn't just some random number. It's a super critical design choice, and it's all about balancing some major trade-offs. On one hand, having that extra freedom, that redundancy, gives a robot this incredible flexibility. It can work in crowded, complex spaces, kind of like we can. But, and it's a big but, every single joint you add makes things way more expensive, heavier, and the math to control it, oh man, it gets exponentially harder.
So in the end, the paradox is solved. A robot's degrees of freedom is a story in 2 parts: the 6 ways its hand needs to move, and the number of joints it has to make that happen. It's not just about where a robot can go, but all the clever ways it can get there. It kind of makes you wonder, right? What other complex systems out there are really defined not by their freedom, but by their constraints?